So what we are working on for today's notes is a few more properties with logs. What they want you to do is whenever you have a log problems, they always want you to simplify it as much as possible. So with that being said, sometimes what they do is they set up examples where they tell you that log of 2 is a. So that means whenever you see the log of 2, they want you to replace it with an a. Here, log of 3 is b. So every time we see log 3, we're going to replace it with a b. And then log 10 equals a 1. So they want us to simplify these expressions that they've given us. So to do that, what we're going to do first is we're going to still follow our normal log properties. So here I have a division. So that means I'm going to subtract my logs. So log of 10 minus the log of 9. It's always your numerator minus your denominator. So right away I see I have a log 10. They told me a log 10 is a 1, so I'm going to replace that with a 1. However, they did not tell me anything for the log of 9. But I do know that I can replace 9 with a 3 squared. It's equivalent. 3 squared is 9. Log rules now tell us that the exponent goes in front. So I have 1 minus 2 log 3, and now I have what they gave me. They told me log 3 is a b. So I have 1 minus 2b. And that would be our final answer for that one. So let's try 60. So again, 60 is not one of the ones they gave us. They gave us 2, they gave us 3, they gave us 10. But if we think about it, 60 can be broken down into 10 times 6. So there we go, we have the 10. But then I have to break down my 6 a little bit more, which would be 3 times 2. So 10 times 3 times 2 is the same thing as saying a 60. So we can rewrite this as log of 10 times 3 times 2. So then using our log properties, whenever things are being multiplied, that means we're really adding them. So log 10 plus log 3 plus log 2. And now we can do all of our substitutions. Log 10 is a 1, log 3 is b, log 2 is a. And that would be our final answer for that one. And then for our last one, again, we have to somehow get them into 2's, 3's, and 10's. So I know 30 is 10 times 3, and 4 is the same as 2 squared. So I'm going to use my division property here first. So log of 10 times 3 minus log of 2 squared. So now I'm going to use my product rule, and at the same time I'm going to use my exponent rule and bring down my 2. So this is log 10 plus log 3 minus 2 log of 2. So now we can go ahead and do all of our substitutions. Log 10 is a 1, log 3 is a b, log 2 is a, so that gives us an a, so that gives us 2a because of this 2 out in front. And that would be our final answer for that one. So here we have another example. They want us to evaluate this statement here when we were given that log a is 2, log b is 7, and log c is 5. So we're going to be replacing some with numbers this time. So I know because of this radical here, this is really a to the 1/2 times b over c squared. Remember, we always rewrite those radicals as our exponents. So we'll do our division rule first. So log a to the 1/2 times b minus log c squared. So now our product rule, these are being multiplied, which means their logs are added. So log a to the 1/2 plus log b minus log c squared. And then our exponent rule, 1/2 log of a plus log of b minus 2 log of c. So we've expanded it out just like what we did last class. And so now I'm going to go ahead and plug everything in. So log a, I'm going to plug in a 2. So I have 1/2 times 2 plus log b is a 7 minus log c is a 5. So 2 times 5. So 1/2 times 2 gives me a 1, plus my 7. 2 times 5 gives me a negative 10. So 1 plus 7 is 8, minus 10 gives me a negative 2. So that's going to be our final answer for that one, negative 2. So again, if log base 3 of 2 equals k, express in terms of k, so we have to figure how to separate these out. So 18, I can do is 9 times 2. So I'm going to get log base 3 of 9 plus log base 3 of 2. So now again, this I can replace with my k because they gave us that over here, that log base 3 of 2 is a k. So that's a k. This I'm going to change to be 3 squared. So that gives me 2 log base 3 of 3. Now we did talk about this a little bit, but there's our rule here. If this number and this number, your base and your answer, if those match, it turns into a 1. So this becomes 2 times 1 plus your k. So 2 plus k is our final answer. Again, to go over this a little bit more, when these are the same, you're saying 3 to what power gives you a 3? Well, 3 to the first gives you a 3. So that's how it's a 1. It's always a 1 when your base and that number are the same. So let's go over here. So for over here, we're looking for 2's. Got to deal with some 2's. So I'm first going to use my division rule. So we got log base 3 of 8 minus log base 3 of 9. So 8, I'm going to rewrite as 2 to the third power. So when I use my log rules and bring my exponents down, I get 3 log base 3 of 2 minus, again, this turns into 3 squared, so we get 2 log base 3 of 3. So based on what they told us, log base 3 of 2 is a k, so this turns into 3k. That 3 stays out in front still. Minus, and again, these two numbers are the same, so that turns into a 1, so 2 times 1 gives us a 2. So that's just 3k minus 2. All right, so down here we got 3 examples. We've got log base 5 of 3 equals an a. They tell us to find log base 5 of 45. So I know 45 is really 9 times 5. So I'm going to do log base 5 of 9 plus log base 5 of 5. So now these two numbers are the same. I know that turns into a 1. Over here, hopefully you're thinking by this point, 9 I can change into a 3 squared. So then my exponent comes in front and I get 2 log base 5 of 3 plus 1. They told me log base 5 of 3 is an a, so this becomes 2a plus 1. And that's our final answer for that one. So over here again, following our rules, these are being multiplied, but I'm going to rewrite this as n to the third, n to the 1/2. So really, what happens here is we can add these exponents together. So we have log base n of n to the 7 over 2. 3 plus 1/2 is 7/2. That's just going with our exponents rules that we've been practicing since day 1. So now this moves in front. So 7/2 log n of n. Now these are letters, but these still match. Your base and that number there, those are the same. So this whole log turns into a 1. So it's 7/2 times 1, which would just be 7/2. Or some people like to write it as 3 and 1/2, but really we want to see the improper fraction. We want to see the 7/2 instead. All right. So this one again, if we're using our rules of exponents, we don't want negative exponents. Those really are not our friends. So this needs to move up. So really, this is just a w squared. So following our log rules, I'm going to bring my exponent in front. So 2 log w of w Our base and that match, so it becomes 2 times a 1, which is just a 2. So that's our final answer for that one. All right, dealing a little bit more with our log graphs. We talked about this a little bit on the first day, so this box up here, this is really just basic review. So if you keep in mind, our basic log graph looks kind of like that. Whereas your basic graph, the domain is always x is greater than 0. Our range is always an element of the reals. The common point for your parent log graphs, it's always going to have an x-intercept of 1 unless you move the graph up, down, left, or right. Any kind of movement changes that. Otherwise, it's always going to be a 1, 0. We have a vertical asymptote. Remember, we usually shorten that down just to say VA at x equals 0. Again, that does change if your graph changes, if you move it around. So then if you have a number right next to x, remember that moves it left or right, and that changes pretty much everything. That changes your x-intercept, that changes your asymptote, and that does change your domain. So you can type it in your calculator and see what the graph looks like. Or you can always just try to figure out in your head just by knowing what the transformation is. So here, given our basic graph, log base 3 of x, this one is a parent graph because it's a very basic form of your log graph. So with that being said, our domain would be x is greater than 0. It'll never touch or cross your y-axis, which is where x is 0. Your range will be y is an element of the reals. Our x-intercept would be at 1, 0. And our vertical asymptote would be at x equals 0. However, if I do this, if I subtract 6, this is just like the transformation rules that we talked about in Unit 3, our functions unit. Subtracting 6 makes it move right 6. It's always the opposite of what you think when you add or subtract from x. Adding, remember, makes it move to the left. Subtracting makes it move to the right. So our graph that we would have, they always normally hit this common point 1, 0, but now it is 6 over, so it's going to hit at 7, 0. So our x-intercept would now be at 7, 0. Now your range would still be y as an element of the reals. That's not going to change. Your range isn't going to change. For our domain, though, again, our domain has been moved over 6. So whereas before it was x is greater than 0, it would now be x is greater than 6 because I moved it over to the 6. And then our vertical asymptote would also move over 6. So y, or x would equal 6 would be our vertical asymptote. So as I said above, your domain, your x-intercept, and your vertical asymptote changed. However, your range stayed the same. So let's take a look at this next one. So for this next one, we are subtracting, that's our change, directly, or we're negating our x. So our transformation rule is if we negated the x, this makes it reflect over your y-axis. If I had a negative out in front, so if I had negative log 2 of x, this would reflect over the x-axis. Negative in front, x-axis, negative with your x is your y-axis. That's just like a little side note for you. So if that's the case, if I had taken it and reflected it over the y-axis, so here's my original graph. If I then reflect it over here, it's going to go this way. So our new y-intercept would be at negative 1, 0. So here, 3 and 4, they want us to find our domain algebraically. So to find it algebraically, what you want to do is whatever's in these parentheses here, you want to set it to be greater than 0 because our original parent domain was that x is greater than 0, and that's when this is normally just an x here. But now you have x plus 2, so you take that whole thing, set it to be greater than 0, then we subtract our 2, So our new domain would be that x is greater than -2. Same thing down here. You take what's in the parentheses. 3x minus 5 is greater than 0. Add my 5. So 3x is greater than 5. Divide by 3. X is greater than 5/3 would be our new domain. And it's always the stuff that's in the parentheses. So if you had log base 3 of 2x minus 1 plus 5, it's still just the stuff in the parentheses is greater than 0. So we would add our 1, divide by 2. So that domain would be x is greater than 1/2. Okay, let's take a look at our ln graphs. So what you want to do is go to your y equals and just type in the ln of x. So in my calculator, I go to the y equals, type in ln of x. No, I don't want to. If we just take a look at the graph, it should look very familiar. It does look exactly like your log graph because it's the same kind of function as your log graph. We just use this one when we have a base of e as opposed to a base that's a number. So if we look at our table, we want just a few points. So we could use the point 1, 0. And then I'll use 2.69315. Let's see here, can we find another good point? Doesn't look likely. So I'll use 3 and then 1.0986. So we'll graph those. 1, 0, 2.6, so we're a little bit more than halfway. And then 3, 1.0986. And we'll draw our graph. So y equals the ln of x. So again, our domain is just like our log graph. X is greater than 0. You have that vertical asymptote in here that we still want to draw in like we do on our log graphs. And that's at x equals 0. So there's our vertical asymptote, x equals 0. Your range, same again as our log graphs. Y is an element of the reals, and your x-intercept is the point 1, 0. So the transformations on your ln graphs are the same as your transformations on every graph. So here they want us to describe the transformation. So that's step 1. They want us to find the domain, the range, the x-intercept, and the vertical asymptote. So for A, because we negate the x, this is a reflect over your y-axis. 2, your domain. So since this time we've reflected it over the y-axis, I've taken this graph and it's now over here going like this. That means that our domain flips and it becomes when x is less than 0. Our range, still y is an element of the reals. Our x-intercept this time changed to -1, 0. And our vertical asymptote has stayed the same. It's still going to be x equals 0. All right, let's go on to B. So this -5, no parentheses around it. So this moves down 5 units. So since it moves down 5 units, your domain is not going to change. It's still going to be x is less than, or x is greater than 0. Range, also not going to change. Y is an element of the reals. X-intercept, we're going to come back to that one in just 1 second. Vertical asymptote, also not going to change. So just sliding it down, your domain, your asymptote, and your range, they all stay exactly the same. The thing that changes is your x-intercept, and that one's kind of trickier to find out. So in this instance, your x-intercept is when your y equals a 0. So if I do 0 equals ln of x minus 5, I tried solving it, so I'll add my 5 over. You kind of get stuck at this point. You're like, oh, how do I get that x out of there? So keep in mind, this is a base of e, so this is going to be e to the 5th equals x. So then you could use your calculator, type in e to the 5th, and you get 148.41316. So your x-intercept on that one is a pretty big change. All right, our last one in this section here. So this one, plus 2, so this moves left 2. So that makes our domain move to the left 2. So x would be greater than negative 2. Our range would stay exactly the same. Y is an element of the reals. Our x-intercept was at 1. Remember, here's my basic parent one, kind of. If I move that to the left 2, it's now going to be at negative 1, 0. And our vertical asymptote also moves to the left 2. So it would be at x equals negative 2. So that's just practicing your transformation rules and everything again that we've been doing already this year. Okay. So now our log rules that we have been practicing, the same rules apply for your ln's. So if they tell you to expand or condense an ln, you follow the same exact ruling. So we always said division first. So if I look at letter A, I'm going to do my division first. So I get ln of x cubed y minus ln of e squared. Then I'll do my multiplication, which happens here. So we get ln of x cubed plus ln of y minus ln of e squared. And then we'll bring any exponents forward. Now, one of the properties they want you to remember is if you are taking the ln of e, that always turns into a 1. So our final answer for this one, I'll write it over here, would be 3 ln of x plus ln of y minus a 2. Just like before with our logs, you always have to evaluate it if you can, and making it a 2, because it was 2 times the 1. Okay, over here, I'm going to first change this so it's an exponent as opposed to a radical. So now I'll do my division, ln of e to the 1/2 minus ln of a cubed b. And so now we will do our product rule, but since there's 2 of them after the subtraction sign, they were both in your denominator. So you want to put parentheses around it, because the parentheses, remember, shows you that they were both in the denominator. So then again, I'll bring my exponents forward, so 1/2 ln of e minus 3 ln of a plus ln of b. And once again, there's that ln of e, so that just turns into a 1, so we get 1/2 minus 3 ln of a plus ln of b. Now keep in mind, you could distribute that negative sign if you wanted to, but you don't have to. Okay, so here we are condensing. They gave us our nice long expanded form. We have to condense this now, so I'm going to take care of exponents first, which I have an exponent of 2 and an exponent of 1/2. So that's going to be ln of a squared minus ln of b plus ln of c to the 1/2. So now, parentheses first, so I'm going to take care of this one first. It's subtraction, which means it's division. So it's the ln of a squared over b plus ln of c to the 1/2. So when this happens, you're saying it's this times c to the 1/2. So the way we would write that is ln of a squared c to the 1/2 over b. So that would be our final answer. And you could change the 1/2 into a radical if you wanted to, or you could leave your answers just like that. Okay, Next step, finding the inverse. Finding the inverse is exactly what we've done before. You want to switch your x and y, and then solve for y. Nothing new here. So I'm going to switch my x and my y. So instead of y equals, I'm going to have x equals log y plus 3 minus 4. So I'm going to add my 4 over. X plus 4 equals log of y plus 3. Now I can't just subtract my 3 because it is attached to the y, which is why we have the parentheses there. So I'm going to take this out of log form. Remember, this is a base of 10 if there is no number written. So this is going to be 10 to the x plus 4 equals y plus 3, the base exponent answer. And now you can subtract your 3 over. So 10 to the x plus 4 minus 3 equals y. That's going to be our inverse there. So let's take a look at our next one again. Finding inverse still. So I'm going to switch my x and my y. And then I'm going to subtract my 2 over, so I get x minus 2 equals the ln of y minus 8. Again, these are attached because of the parentheses, so I can't do anything yet except take it out of ln form. If it's an ln, that means it's a base of e. So it's going to be e to the x minus 2 equals y minus 8. Add my 8 over, and there's my inverse form. As always, guys, if you have extra questions or this didn't make much sense and you still need more help, you can always come see me after school or in a study hall.